Okay, hello everyone. This is chapter 8, estimation part 2. Okay. Chapter 8.4 is evaluating the goodness of a point estimator. And in previously in chapter 8.2, we learned about mean square error, which is another way of uh, checking the goodness of the point estimator, and the MSE is expected value of zeta hat minus zeta squared term. So this is MSE, and this one is also another way of evaluating goodness of point estimator. Let's read about this. Definition 8.5. The error of estimation E is the distance between the estimator and its target parameter, that is, the absolute value of zeta hat minus zeta. And so uh, both for MSE and error of estimation, what we want is we want to minimize the difference between zeta hat and zeta. Um, However, the MSE, the term MSE, this is constant, because we are taking expectation on the random variable, and so this is constant term. And but however, the epsilon, it is still random variable. It is the theta hat is a random variable because it is function of samples. So our estimate theta hat, this can be derived from the samples. For example, estimate for mu is x bar. X bar is averaged value of or random samples and n number of random samples. So in that way, zeta hat is a random, again random variable, and so we can do the probabilistic inference, something like this. Probability of error of estimation is less than b, and then probably we can um, calculate this probability based on the probability distribution of the random variable. B is as a probabilistic bound on the error of estimation. So the situation can be visualized as figure 8.4. As we know, the zeta hat is a random variable. So zeta hat have a distribution. Like, let's say zeta hat have distribution like this, and then we can calculate the probability of zeta hat is bounded by b, yeah, like this. So the probability of our zeta hat is bounded by b, and probably we can get the probabilistic bound for the estimator. Okay, let's move on to example 8.2. A sample of n equals 1000 voters randomly selected from a city showed y equals 560 in favor of candidate Jones. Estimate p, the fraction of voters in the population favoring Jones, and place a two standard error bound on the error of estimation. Okay, so the first one is estimate p. So estimate p, which is p hat, and actually this is uh, 560 divided by 1000. Why is it? And here we have n number of 1000 voter samples, and we can say each of each of voters is Bernoulli triers. So we can think that it's B1 to B 1000, and if it is 1, they voted. This guy voted for candidate Jones, and okay. And the next question is the fraction of voters in place a two standard error bound of the on the error of estimation. So next thing is we want to provide two standard error bound, and to do that we should check the distribution of p hat, and actually this p hat is b bar. If we think that each of these samples are Bernoulli trials, then p hat, it is actually b bar, the average value of the Bernoulli trials. This is actually something like this. And so by using a central limit theorem, we can derive that p hat follows normal distribution with mean p and variance p 1 minus p divided by n. And so using central limit theorem, and and so and also to estimate the standard error. So this part, square root of this thing is standard error. The standard error for p hat, as we can also say standard error of p hat. This is square root of p 1 minus p over n, and to estimate this thing, to estimate standard error of p hat, we can use n over p hat 1 minus p hat. Okay, and what would be the probability of two standard error bound? So probability of p minus p hat is inside of two standard error bound. Two standard error bound is about 95% from the normal distribution. And so we can, if we can calculate this, then we will get the bound for two standard error bound. So so we can say p minus 0.56 absolute value of this thing is bounded by 2 times we need to estimate standard error estimate, and this thing is to calculate it, this is 0.56 times 0.44 divided by 1000, and actually 2 times of this thing. Using calculator, this is approximately 0.03, and so this is 0.03, and so if we solve it for p, then we can get p is bounded from 0.53 to 0.59. So this is our answer. Okay, let's move on to example 8.3. A comparison of the durability of two types of automobile tires was obtained by road testing samples of N1 equal N2 equal 100 tires of each type. The number of miles until wear out was recorded, where wear out was defined as the number of miles until the amount of remaining tread reached a pre-specified small value. The measurements for the two types of tires were obtained independently, and the following means and variances were computed. So here's the information. And estimate the differences in mean miles to wear out, and so this is the first question, and place a two standard error bound on the error of estimation. So for the first question, estimate the difference in mean mile to wear out, which is actually very easy. Y1 bar minus Y2 bar. So Y1 bar minus Y2 bar would be our estimate estimator for the difference in miles, mean miles to wear out, and place a two standard error bound on the error of the estimation. And to answer this, we need a distribution of y1 bar minus y2 bar. And actually, by using central limit theorem, we know the distribution of y1 bar and y2 bar. The distribution of y1 bar is it follows normal distribution with mean mu1 and variance sigma 1 square over n1. So this is distribution for y1 bar, and for y2 bar it is normal mean mu2 and sigma 2 square over n2. And so, if y1 bar follows normal and y2 bar follows normal, then sum of the y1 minus y2 bar, y1 bar minus y2 bar, actually also follows normal distribution, which is mu1 minus mu2, and variance is sum of them, sigma 1 square over n1 plus sigma 2 square over n2. And so from this distribution, we can construct two standard error bound. So for the probability of y1 bar minus y2 bar, probability of y1 bar minus y2 bar minus mu1 minus mu2 can be bounded by two standard error estimate for y1 bar and y2 bar. And this probability would be 0.95, and from here we can get the bound for mu1 minus mu2. So y1 bar minus y2 bar, that is y1 bar minus y2 bar is 1300, and so 1300 minus mu1 minus mu2 absolute value is bounded by 2 times estimate for standard error is 2 times square root of 1440000 over 100 plus 1960000 over 100, and this value is 368.8. Okay, so if we solve it, then we will get we will get bound for mu1 minus mu2. So mu1 minus mu2 is bounded by 1668.8 and minus 368 is 931.2. Okay, so this is bound for mu1 minus mu2. Okay. Let's try to solve one exercise problem, which is 8.36. If y1, y2, and yn denote a random sample from an exponential distribution with mean theta, then expected value of yi equals theta and variance of yi equals theta squared. And thus, the expected value of a y bar is theta and variance of y bar is theta squared over n. And or the standard error of y bar is theta over square root of n. Suggest an unbiased estimator for theta. Suggest an unbiased estimator for theta. And provide an estimator for the standard error of your estimator. Okay, so this is problem 2. The first one is suggest an unbiased estimator for theta. And actually, we can directly make our estimator using this. Since expected value of y bar equals theta, we can propose our unbiased estimator as theta, y bar. Y bar is our unbiased estimator because expected value of y bar itself it's theta. So y bar is unbiased estimator. And second, provide an estimate for the standard error of your estimator. And standard error of y bar, this is theta over square root of n. So provide an estimate. To estimate this, our estimator for theta, our unbiased estimator for theta is y bar. So we can provide our estimate is y bar divided by square root of n. So this is our estimate for the standard error of our estimator. Okay. And homework for chapter 8.4 are these. Okay, chapter 8.5 is about confidence interval. So for the confidence interval, we need two properties. First one is it should contain the target parameter theta, and the second is the interval should be relatively narrow. Okay, and this is just notations. The upper and lower endpoint of a confidence interval are called the upper and lower confidence limits. So if we have this kind of distribution, and if we have if we say this is our confidence interval, then this is upper confidence limit and this is lower confidence limit. And also the probability that a confidence interval will include theta. So this is theta hat, axis of theta hat, and the probability of theta hat is each endpoint would be certain probability, and the probability that a confidence interval will include theta so is called the confidence coefficient. So this is not theta, theta. Okay, and actually the situation is something like this. The probability of theta hat L is greater than theta is greater than this thing and less than this thing. So this is lower confidence limit, and this is upper confidence limit, and this is the confidence coefficient. Okay, and we can have one. We can just have one. Sometimes we just need a lower confidence limit, and sometimes we only have upper confidence limit. One very useful method for finding confidence interval is called the pivotal method. it is a function of the same measurement and the unknown parameter theta, where theta is the only unknown quantity. Each probability distribution does not depend on the parameter theta. Um, it's not uh, um, written very concisely, but we will explain these what these means from the following examples. Okay. Okay, let's move on to example 8.4. Suppose that we are to obtain a single observation y from an exponential distribution with mean theta. Use y to form a confidence interval for theta with confidence coefficient 0.9. Okay, and to use the pivotal method, let's let our u as y divided by theta, and then the density function for y is this. This is exponential distribution with mean theta. So this should be the distribution function for y, density function for y. And if we define our y as y over theta, then by using the method that we learned from the first semester, we can derive the distribution of u, and which is this one. And we can check these two conditions. So the u, it is a function of the sample measurement y, and the unknown parameter theta, y over theta. So y over theta is function of the sample measurement and the unknown parameter theta, where theta is the only unknown quantity. So this is the first part is true, and the second part, each probability distribution does not depend on the parameter theta. The probability distribution, this thing, does not depend on parameter theta. So those two conditions are hold. So let's proceed. Find probability of A greater than let's find this situation. So using the graph, this graph shows the exponential distribution, and um, and we want to find the probability any A and B to meet this condition. We want to find any A and B that meet this situation. Then we can use the pivotal method. And for the convenience, we will let this condition. So the probability of u is less than a is 0.05, and probability of u is greater than b is 0.05. Then uh, this condition will hold. So we will calculate this a and b. From the previous slide, we decided to use this quantity. Probability of y is less than a equals 0.05, and probability of u is greater than b is 0.05. And if you solve this, we can calculate a and b. So for this one, integration of this thing is minus e to the minus u, and integration is from 0 to a, and this is minus e to the minus a plus 1, which is 0.05. And so e to the minus a is equal to 0.95, and so a is minus ln 0.95. Okay, and also for b, this is e to the minus u, minus e to the minus u from b to infinity, which is e to the minus b. And this, since this is 0.05, we can conclude that b is equal to l, and take ln and take minus here, minus ln 0.05. Okay, and if you use your calculator to calculate these values, you can find A is this thing and B is this thing, and since U is Y over theta, so so the probability of 0.051 return Y over theta 2. 2.996 is 0.9, and actually this part we can re-express this as firstly we theta over y, then it's 2.996 over 1 and 0.051, and actually if we multiply y to both sides, then this is probability of y over 2.996, and this is possible because y is greater than 0, so theta and y over 0.051. Okay, so now we derive the confidence interval for theta. The probability is 0.9. Okay. Let's move on to example 8.5. Suppose that we take a sample of size n equals 1 from a uniform distribution defined on the interval from 0 to theta, where theta is unknown. Find the 95% lower confidence bound for theta. Again, let's define our u as y over theta, and for y, for density function for y, this is 1 over theta. Density function is 1 over theta from 0 to theta, and otherwise 0 otherwise. And to derive this one, previously I skipped it. Previous example 8.4 I skipped it, but to for this is from mathematical statistics 1 course, and actually this can be derived as this formula. To remind your memory, this is dy du. This is actually Jacobian coefficient, and to calculate this Jacobian, you know that y equals theta u, so dy du is theta. Dy du is theta, and so fy, this one is 1 over theta, and that times theta equals 1. So the density for this thing is this one. Okay. And to find 95% lower confidence bound, we have this. We want this A. Probability of U is less than or equal to A is 0.95. And from the uniform distribution, by integration of the uniform distribution from 0 to A, dy equals 0.95, then A should be 0.95. So integrating this thing, this is y0a, and this is a, and a equals 0.95. Okay, so we can infer that the probability of y over theta less than or equal to 0.95 is equal to 0.95, and so probability of theta over y greater than or equal to 1 over 0.95 is 0.95, and let's multiply y each side. Then this part would be the lower bound for theta. Y over 0.95 is 95% lower confidence bound for theta. Okay. And the homework for chapter 8.5 are these. Okay, so this is the end of the lecture for today, and see you next week. Thank you.